Alright guys, I'm going to get started. So what are we going to be looking at in today's class? So in today's class, we are going to be looking at emissions modeling primarily. We're going to be looking at the type of emissions that people care about for most type of engineering applications. It can be IC engines, it can be gas turbines. These are the primary pollutants that people care about. Okay, and with respect to background, right, I don't think I have to say why we care about emissions. Emissions can cause a lot of problems, so we need to make sure that it's kept under control. All right, and with respect to devices like IC engines or gas turbines, it is possible to measure emissions with good amount of time resolution, but then the process tends to be very costly, and sometimes you cannot get all the data because of the nature of these devices. There is combustion going on, so either if you have to measure some real hardcore data, your sensors that you use to measure these emissions, it's going to be like a one-time use. I mean, they get burned up and that's it. And in certain cases it might be impossible to measure also. Okay, so from a computational standpoint, it is very important to understand the important emissions, how they are formed, so that we can try to predict these emissions using a computer. So primary emissions, again with respect to IC engines that we care about, is NO. NO is called as nitric oxide. Okay, it's a very dangerous pollutant. NO2, it's called as nitrogen dioxide. And oftentimes we might have heard the term NOx, NOx. So NOx is basically a combined name. So if X is 1, then it's nitric oxide. If X is 2, it's nitrogen dioxide. So people commonly refer to them as NOx. The second thing is unburnt hydrocarbons. Right from the start of the class, we have told several times that the fuel is a hydrocarbon. Sometimes what's going to happen is, if your combustion is not taking place correctly, then there are misfires, then a large amount of fuel vapor is going to get out through the exhaust pipe and it's going to mix with the atmosphere. And this is called as unburnt hydrocarbons. So this also needs to be kept in check. There are several methods that are available to keep these things, but it is good to know what these emissions are. The next thing is particulate emissions. So the idea behind particulate emissions is, these are emissions where you actually get particles. Now these particles are really, really small. They are on the order of nanometers. Okay, these are very, very small. And the problem is they can cause serious health hazards. These particles are so small that they can get into the human, like it can cross your respiratory system very easily and can cause long-term damage if you have prolonged exposure. And oftentimes you might have heard of the term soot, SOOT, soot. Soot actually comes under the classification of particulate emissions. There are other types of particulate emissions which we will see, but soot is kind of the most important thing. In addition to that, there are some fuels where alcohol is contained. Okay, so the fuel contains alcohol, and in those cases you will get aldehyde emissions. These are really rare. I mean, if you don't have alcohol in your fuel, then you don't get them. Just for sake of completeness, I'm putting it. Now, historically, both gasoline and diesel fuels used to have a lot of sulfur. Now, the problem with this sulfur is that when it reacts, when combustion takes place, you get sulfur dioxide, SO2, and the sulfur vapor, when it mixes with water in the atmosphere, it forms sulfuric acid, which is a very bad acid, as you might have all studied, and it causes acid rain, and which is very bad. But the last two problems, both aldehyde and sulfur emissions, are not that bad, because especially with respect to sulfur emissions, the whole industry has shifted towards low sulfur or ultra low sulfur fuels. You might have heard of something called as ULSD, ultra low sulfur diesel. And similarly with gasoline, the sulfur percentage has been brought down very, very low. So these are no longer very big problems. So how much emissions do you get? Okay, and what is it that people are trying to regulate? So just to give you an illustration, right? Typically, emissions are measured in several units. ppm is there, which is parts per million. But the most intuitive way to think about it is grams of pollutions per kg of fuel, something like this. So kg of emissions per kg of fuel, the emissions are usually not that much, so we say grams of emissions per kg of fuel. So if you take a typical automobile that is used for transportation, right, basically your car, the amount of NOx it produces. All right. So if you have 1 kg of fuel, 20 grams of that is going to be converted as NOx. Okay. So this actually gives you a very good idea of how much emissions gets produced. Now with NOx and CO2, year on year there is strict government rules, at least in the US, to basically bring it down. CO is carbon monoxide. So carbon monoxide is produced in your engines when there is less oxygen. When you don't have a lot of oxygen, you have excess fuel. Carbon monoxide gets produced a lot. In fact, for 1 kg of fuel, about 200 grams of CO is produced, which is a lot. And in most modern cars, this CO is converted to CO2. Okay, so that is something you need to remember. Unburned hydrocarbons is again very similar to NOx, 25 grams per kg of fuel. Particulate emissions, we'll talk about it, because particulate emissions, there is 5 grams per kg of fuel. But more importantly, people are interested in how big the particulate matter is, because you can use some kind of a filter to catch it. But if the particulate matter is really, really fine, it can actually get through the filter and it can render the filter useless. All right. So these are kind of the emissions that we typically care about. Like I said, these two things I'm not going to be worrying too much about, both aldehyde and sulfur. So the other thing that you need to remember is, where do these emissions occur? And for demonstrating that, what I have is, I have a very simple diagram of an engine. So, this is actually, you're looking at the engine from the front. So everything is going to be looking like a rectangle. So this right here is your engine liner. So the liner is the surface within which your piston is going to move up and down. And then you have your piston. And between the piston and the engine liner, you have something called as the crevice volume. So a crevice is nothing but a small gap, right? In English, that's what crevice means. So, the same thing applies here. Between the piston and the liner, there is like a very small gap, usually in the order of microns. And what can happen is, sometimes the fuel can actually enter into this gap, and that can cause some emissions. So that is why I'm considering this gap. Okay. So what's going to happen? So let us say combustion takes place. So here, this black line that I've drawn here, let us say that is the flame front. So inside that you have burnt gases, and outside you have unburnt gases. So the burnt gases are at a higher temperature, right? Now, when temperature is going to be high, that is going to promote the formation of NOx and also the formation of carbon monoxide. Again, we are talking about a spark ignited engine here, so we are assuming that things are premixed. So one thing that can actually happen is, if it is a PFI engine, if it's a port fuel injected engine, or if it is an engine that has a carburetor, the fuel, basically enters into the combustion chamber very early so that it gets enough time to mix. However, in this process, some amount of fuel can get trapped inside the crevice volume, and as the piston moves up and down, it is slowly going to get released into the exhaust, and it is going to come out from your tailpipe. When I say tailpipe, is basically your exhaust of your car or bike. And that is what is called as unburnt hydrocarbon. Unburnt hydrocarbon is basically fuel that is getting wasted. However, nowadays what's happening is, like all the automotive companies have something called as a carbon canister. So a carbon canister is a device that will take in these unburnt hydrocarbons. It will get the fuel, and then from the filter, what we do is we connect it back to the intake system so that the fuel is not getting wasted. It is fed back into the combustion chamber so that it is getting used. So NOx and CO, it's very important to understand that they get formed when temperatures are high. Because like I said, again, at the end of the day, these are all chemical reactions. You need some amount of energy to make sure that the chemical reaction progresses, and that is typically done through temperature. So emissions as a function of equivalence ratio in a SI engine. So this is a very important point. So one thing again here to understand this plot, a little bit of knowledge about engines is required, but I think it's okay. I can explain that part. So typically you want your IC engine to operate at stoichiometric ratio or slightly rich. So here what you're actually looking at is, for example, if I look at this profile, I'm looking at NOx as a function of equivalence ratio. So NOx is highest at close to stoichiometric, and then if it is a lean mixture or if it is a rich mixture, NO gets reduced. Okay, you get like a bell-shaped curve. Now here you can see that there are two curves. Okay, what does that mean? Well, that is basically the bandwidth. So that is the range within which your NOx varies. Again, this is data that has been measured. So for several types of engines. different engine sizes and all that stuff, and we are looking at a cumulative plot. So that is why there is a range here. See, one of the things you need to remember is that the value for the NOx, it depends upon the equivalence ratio, okay, and it depends upon the maximum temperature. If your temperature values are less, you don't get a lot of NOx. So and at stoichiometric, that is where your burning is going to be most efficient, and that is where the temperature rise is going to be the most highest. And that is why close to stoichiometric, you have maximum temperature and maximum NOx. Away from stoichiometry, your max temperature drops and hence NOx also drops. With respect to CO, okay, what is like I said, carbon monoxide is formed whenever there is less oxygen, or to put it other way, whenever there is more fuel. So that is why when my equivalence ratio is less than 1, which means it is lean, I have excess air, which means I have excess oxygen, CO is less. But then as I'm increasing the amount of fuel, my equivalence ratio is going beyond 1, which causes CO to increase rapidly. So this plot is quite straightforward. An interesting trend can be observed with hydrocarbon emission. So even with hydrocarbon, let us take a look at this linear range. So in this linear range, what's actually happening is, as you're putting more and more fuel and less air, more fuel is going to be remaining unburnt, right? It's going to get trapped more, it's going to not burn, and it's going to result in higher hydrocarbon emissions. However, if you look at here, you see that up to a particular point, hydrocarbon emissions reduces and then it increases. What do you think is going on here? This you need to be able to answer based upon whatever you learned from the combustion course. Why do you think this is happening? What's going on is, as you basically keep on decreasing the amount of fuel, right? Up to a particular point, it's going to work. And unburnt hydrocarbon, it's definitely proportional to the amount of hydrocarbon that is originally present, which is the amount of fuel. So when you're decreasing your fuel, initially your unburnt hydrocarbon emission is going to decrease. But at some point, you are basically in a zone where your combustion is unstable, which means combustion does not take place all the time because you have more air and less fuel. So it's all chemical kinetics. So there's a lot of uncertainty. Sometimes things will burn and sometimes things will not burn. So when things do not burn, the fuel is directly exhausted, and that contributes to significant amount of unburned hydrocarbons. And that is why you see this increase. Okay, so this is an important trend. And one of the reasons why you need to understand these graphs is, it is based upon these type of graphs that engineers design emission controls. So when I say emission controls, in your car or in any type of engine, there is something called as the electronic control unit, which controls the different parameters in your engine, like the fuel rate, the amount of fuel to inject, the intake pressure. It tries to control so many things because it has to make sure that your emissions are within what is allowed. Okay, so emission control is a very big problem because of complex phenomenon like this. We still haven't looked at soot. If you looked at soot, it's going to make the problem more complex.